Okay, I was foiled by the good old loss of power again. So we're going to make part two. Now it's part one and part two. How much snow is on the slope after 5 hours? Remember that the function up here can tell us the amount of snow. So after 5 hours, we start with our initial amount of 50 cubic yards. Then it accumulates, it adds from the snow machine from 0 to 5, this guy, but then we lose to melting over those 5 hours. So we subtract it. You can do that in your calculator because, again, we have these in Y1 and Y2. You get 95.335 cubic yards. That is an amount because 50 is an amount, and then these integrals represent a change in amount. So we have an amount. They're no longer rates. When we integrate them, we take the rate off them. All right, suppose the snow machine is turned off at time t equals 10. Write but do not solve an equation that could be solved to find the time, capital K, when the snow would be melted. All right, so we turn it off at time 10. So at time 10, there is 183.193. That's how much snow there is at that moment. So let me see here. Yeah. Okay, so you can figure that out first, and that's where we start. Then we want to subtract. If we turn off the snow machine, we're not adding any more snow. Now it's just melting. From the 10th hour to whichever hour K, which we don't know, we're going to find of meltage. And there would be no more snow left, so the amount of snow would equal 0. When you integrate this, you'll get some kind of function that has K in it, and you can solve for K. But they're not asking us to solve. They're just saying write the equation that you would solve for that. Okay, let's move on to an AP problem here. All right, so use the data from the table to find an approximation for r prime of 45. Show the computations that led to your answer. Indicate units of measure. Okay. So we're going to estimate or do an estimate for r prime of 45. So that's going to be approximately the average rate of change between 40 and 50, right? So we're going to go r of 40 minus r of 50 all over 40 minus 50. And that's going to equal 40 minus 55 over negative 10. So it's going to be 1.5. And what that's going to be is gallons per minute squared, because r was already gallons per minute. So r was already a rate. So the derivative of a rate is a rate of a rate, which is an acceleration. So that's A. Part B says the rate of fuel consumption is increasing fastest at time equals 45 minutes. What is the value of r double prime of 45? Explain your reasoning. So they're telling us that right through here is when it's increasing the fastest. That's where r is increasing the fastest. So I guess what we would say here is that r double prime at that point would be equal to 0, because if r is increasing the fastest, that means r prime has a maximum. So we'll say that since r is increasing the fastest, then I should say at 45, then r prime of t has a maximum at t equals 45. Therefore, this means that r double prime of t equals 0 at t equals 45. They asked it as r double prime of 45, so I could just write it that way. Therefore, r double prime of 45 equals 0. We know that that second derivative there has a 0 because the first derivative has a maximum. So it's got to cross the axis. The derivative, where there's a maximum, then the derivative of that has to cross the axis, changing from positive to negative. All right, C. C says, approximate the value from 0 to 90 of R of t using a left Riemann sum with the 5 subintervals indicated from the data on the table. So we're going 0 to 90. So we're using all of these. We're using 1, 2, 3, 4, 5 subintervals. So are they uniform width? It goes up by 30, then it goes up by 10. They're not uniform width, so I can't factor out that width. So we're going to say the integral from 0 to 90 of R of t dt can be approximated by the width times the height. And now we're doing the left Riemann sum, which means we're going to throw out the rightmost or the uppermost one. We're going to start with the lowest one and use 20 on our first rectangle as the height. The next width is 10 units, and its height is 30. You can pause it here and crank this out. I'll do the same so we don't waste time watching me fumble back and forth between the graph and writing these down. All right, so this is what I got. I got 3,700 as my approximation. Do they ask for units? Nope. Explain your reasoning. What do I have to explain my reasoning about? Is this numerical approximation less than the value? Explain your reasoning. This was a left Riemann sum. The values are increasing, so yes. We're going to say yes. This is an under approximation. And we would say because R is increasing on the interval, what was it? 0 to 90. All right, because it was increasing, this is an under approximation. Let me show you how you know that. When it's strictly increasing. Okay, so a strictly increasing function. If I do left-hand sums, that means I use the left side of the rectangle. Right, as I draw my rectangles, I'll go here where it's a little more obvious that it's increasing. When I make the left side of the rectangle hit the curve, they're going to be under. Okay? So a left hand, when it's increasing, will be under. If we did right hand sums, when I draw my rectangles, if I want the right side of the rectangle to hit the curve, then it's going to be an over approximation. And then that flip-flops if the function were decreasing. What are we on? Part D here. And this isn't even the last one. Oh my gosh. All right, where are we on time? Oh, this is part 2 though. Yeah. All right, so on the interval 0 to 90, explain the meaning of these two things in terms of fuel consumption. So let's start with 0 to b r of t dt. So they want us to explain what that means. So R was published as a rate, right? So it told us that R was gallons per minute. So if I integrate the rate, that takes the rate off it, and we're just going to do gallons. And it's not how many gallons there are. It's, we'll say the total or the change or whatever. So we can say is the change in the amount of gallons for the first B minutes. Or you can say it's how much gas they've used. It's not how much gas is left, but it's the change in the amount of gas. I've said that so many times. This stuff can get confusing, so I'm just going to keep repeating myself. Okay, now how about 1 over b from 0 to b, r of t dt. So if we're going from 0 to b, this is the length of the interval. So while this part is the amount of change. We're then dividing by, and we're turning it back into a rate. So this is the average rate. So this is the average value of the rate, because it was published as a rate. It stays as a rate of fuel consumption in gallons per minute during the first B minutes of the flight. Okay, last one. I did all these videos in one day. I am pretty beat. This is my last example for this unit. Holy cow, it's taken like 7 hours to do all these answer keys and videos. Maybe more. I am fried. Okay. Particle is moving along a straight path. The velocity of the particle is shown in the table below for selected values of t and velocities at a maximum, blah, blah. You can read that to yourself. So this table gives us a velocity. Okay, part A, using the midpoints of 5 sub-intervals of equal length. So we've got 1. I got to charge the pen. What's new? Last charge. I'm going to pause it. All right, so we're going to use the midpoints of 5 sub-intervals to approximate that value. So 1, we're doing midpoint, so we're going to skip over that guy. These should all be midpoints and of equal width, which they are. Okay, so here we go. 1 over 30 times 0 to 30 v of t dt can be approximated as 1 over 30 times. We've got our widths are always 6, so we're going to be times 6, and then each height, and we're using the midpoints, the height of the midpoints. So it's those guys. So 7.5 plus 12.5 plus 13.5 plus 14 plus 13. We do this number out, and we get 12.1, and that's going to be in meters per second, because this was in velocity, was measured in meters per second. When we do this integral, which is this part forward, right? That's going to give me the amount of change in meters, but then we're dividing by change in time, so we're back to meters per second. So what does this represent? This is the average velocity from time t equals 0 to t equals 30. Let's look at part B. Part B says to find the average acceleration of the particle over the interval 6 to 18. Express your answer using correct units. So we're going to do 1 over the length of the interval from 6 to 18. And they want the average acceleration. So we know for this one, so it's going to be 1 over 12 times the integral of acceleration. Well, when we integrate, do the antiderivative of acceleration, we get velocity. So it's going to be v of 18 minus v of 6. So it's going to be 1/12 times that. That whole thing works out to about 1/3. And that is finding our average acceleration. So that's going to be in meters per second squared. I know that when I do average value, right, I've got acceleration. Remember, integrating acceleration would give me a velocity. So that would, and it wouldn't tell me what the velocity is. It would give me the change in velocity over that time period. But then we divide by time, and now it's so the velocity was meters per second, but we divide by time again, so we're dividing by seconds again. So it's meters per second. So that's why it's meters per second squared. We're back at an acceleration. Another way to think about it. Let's go for C. Says find an approximation of v prime of 6. So to approximate v prime of 6 with a table of v's, we're going to do the slope of the secant line. If we're going to approximate 6, we're going to use the values on either side of it. So we're going to say that that's going to be v of 3 minus v of 9 all over 3 minus 9. That's going to be 7.5 minus 12.5 all over negative 6. That works out to be 5/6, and that's going to be meters per second. That is v prime of 6, so that's going to be the derivative of velocity, so it's going to be meters per second per second. Remember that velocity here is measured in meters per second in the numerator, and then we're dividing by change in seconds in the denominator. D is find the left-hand approximation of two subintervals. We're going from 3 to 9. Right, so we're only going from 3 to 9. We don't need those. We don't need that. 2 intervals. We're doing a left-handed one, so I'm going to throw out the rightmost height, and I can use these two as my heights. My widths are 3 every time, so we're going to say that the integral from 3 to 9 of v of t dt can be approximated. The widths were 3, and our heights were those two heights I circled, 7.5 and 10.1, 52.8. Now we're integrating a velocity, so we're integrating meters per second, just becomes meters. That is not the position, it's the change in position over that interval from 3 to 9. So then what do they want us to do with that? Well, I found that. Then use the value to find the position of the particle at t equals 3 seconds if the position is at 9 seconds is 60. So they're telling us that the position at 9 seconds is 60. They want us to find the position at 3 seconds. So we can say that the integral from 3 to 9 of the velocity would be equal to the position at 9 minus the position at 3, and we know that's equal. We just calculated or estimated that to 5.28 meters. So S sub 9 is 60 minus, so I'm going to come down here, S of 3 equals 52.8. If I add S of 3 to both sides and then subtract 52.8, I'll get 7.2, and that is in meters, and that is a position. The position at 3 is 7.2 meters. I think that's everything. I am done.